Welcome to this problem walkthrough. Today, we'll be tackling problem number 256, Paint House. This is a classic dynamic programming problem that challenges us to minimize the cost of painting houses while adhering to specific constraints. Let's dive in and explore the approaches to solving this problem. In this problem, you are tasked with painting a row of n houses, where each house can be painted one of three colors: red, blue, or green. The cost of painting a specific house with a specific color is provided in the form of a costs matrix. For example, costs I0 gives the cost of painting house I red, costs I1 represents the cost of painting it blue, and costs I2 is for the green color. Your goal is to paint all the houses while ensuring that no two adjacent houses have the same color. Additionally, you want to minimize the total cost of painting all the houses. If there are no houses to paint, that is, if n is 0, you should return 0 as there is no cost incurred. The input to the problem is a 2D list called costs, where costs ij represents the cost of painting the ith house with the jth color. Here, I ranges from 0 to n1, and j can be 0, 1, or 2, corresponding to red, blue, and green respectively. The number of houses, n, is the length of the costs list, and each house has exactly 3 color options. The output of the problem is a single integer, which represents the minimum cost required to paint all the houses such that no two adjacent houses share the same color. To better understand this, let's go through the first example. Suppose the input costs matrix is 17, 2, 17, 16, 16, 5, 14, 3, 19. In this case, the optimal way to paint the houses is as follows: paint house 0 blue with a cost of 2, paint house 1 green with a cost of 5, and paint house 2 blue with a cost of 3. This ensures that no two adjacent houses have the same color, and the total cost is minimized to 2 plus 5 plus 3 equals 10. Therefore, the output for this input is 10. Now, consider another example where the input costs matrix is empty, meaning there are no houses to paint. In this case, there is no cost incurred, so the output is 0. Finally, if we look at an example where there is only one house, such as costs equals 7, 6, 2, the optimal solution is to paint the house green since it has the lowest cost of 2. Therefore, the output in this case is 2. These examples illustrate how the problem handles different scenarios, from no houses to a single house and beyond. There are a few important constraints to keep in mind while solving this problem. First, the length of the costs array is equal to n, the number of houses. The value of n ranges between 1 and 100, meaning there can be up to 100 houses. Each house has exactly 3 color options, so costs length is always 3 for all valid indices I. Additionally, the cost of painting any house with any color is between 1 and 10,000. You should also account for edge cases, such as when there are no houses or only one house, and ensure that your solution respects the constraints on costs, even when they are at their maximum possible value. To solve the paint house problem, we began by exploring two primary approaches. First, the brute force approach. The intuition here is straightforward. For each house, we consider every possible way to paint it while ensuring no two adjacent houses share the same color. For instance, if you're painting house I, you have 3 choices: red, blue, or green, but you must ensure the color differs from the previous house. By recursively calculating the total cost for all combinations, we can eventually find the minimum cost. However, this method is highly inefficient because it repeatedly solves the same subproblems, leading to exponential time complexity of 3 to the power of n. The space complexity is n, due to the recursion stack, which is another limitation. Instead, we can use a dynamic programming approach to improve efficiency. Here, we store partial results to avoid redundant calculations. The key idea is to define dp ij as the minimum cost to paint up to house I with color j. The transition relation captures how the cost of painting a house depends on the cost of painting the previous house with a different color. Specifically, the cost for house I with color j equals costs ij plus the minimum cost of painting house I1 with any of the other 2 colors. This systematic approach leverages overlapping subproblems and optimal substructure to minimize computational effort. Based on this dynamic programming formulation, we establish a base case. The cost of painting the first house with any color is simply the associated cost, so dp 0j equals costs 0j. From there, we iteratively build the solution for each subsequent house using the transition relation. The final solution is the minimum cost of painting all houses, which is the smallest value among dp n1 0, dp n1 1, and dp n1 2. In terms of complexity, this approach is highly efficient. The time complexity is O(n), as we compute the cost for each house in each color exactly once. The space complexity is O(n*3) for the dp table, but we can optimize further to O(3) by storing only the last row of calculations. This optimization reduces memory usage significantly without compromising the correctness of the solution. Ultimately, we chose the dynamic programming approach over brute force due to its clear advantage in efficiency. The realization that we could break the problem into overlapping subproblems and solve them iteratively was a critical insight. By focusing only on the transitions between states and maintaining minimal storage, we further improved the practicality of this solution. The dynamic programming approach provides the ideal balance between simplicity and efficiency. By avoiding redundant calculations and focusing on solving each subproblem just once, we achieve a significant reduction in both time and space complexity. This makes it perfectly suited for the painthouse problem, even for large input sizes. With its linear time complexity and minimal space usage, the DP solution is not only optimal but also elegant. It highlights the power of breaking down complex problems into smaller, manageable subproblems, and systematically solving them in a way that scales efficiently. This approach encapsulates the essence of dynamic programming and demonstrates how we can leverage it to tackle real-world optimization challenges effectively. In this problem, we aim to minimize the total cost of painting a row of houses, where each house can be painted in one of three colors, like red, blue, or green. There's an important constraint: no two adjacent houses can share the same color. The cost of painting each house in a specific color is provided, and our goal is to determine the minimum cost to paint all the houses while staying within the rules. To achieve this, we use dynamic programming. First, we represent the painting costs in a 2D list, where costs I, j, gives the cost of painting house I with color j. Then, we define dp I, j, as the minimum cost of painting up to house I with house I painted in color j. The recurrence relation ensures no two adjacent houses share the same color by adding the cost of painting the current house to the minimum cost of painting the previous house in a different color. This framework allows us to systematically calculate the minimum cost while adhering to the constraints. To begin solving, we establish the base case. For the first house, the cost of painting it in any color is simply the given cost of that color. For example, dp 0, 0 is the cost of painting the first house red, dp 0, 1 is the cost of painting it blue, and dp 0, 2 is the cost of painting it green. From there, we calculate the costs for the subsequent houses using the recurrence relation. For any house I, the cost of painting it red is the cost of painting it red plus the minimum cost of painting the previous house either blue or green. Similarly, the cost of painting it blue depends on the minimum cost of painting the previous house red or green, and for green, it depends on red or blue. This ensures that no two adjacent houses are painted the same color. Finally, after calculating the costs for all houses, the result is the minimum value among the costs of painting the last house in any of the three colors, as this represents the minimum total cost. There are a few key insights that make this algorithm efficient. First, by using dynamic programming, we avoid redundant calculations by storing intermediate results in a DP table, saving computation time. Second, the algorithm employs a greedy approach at each step by selecting the minimum cost for valid color transitions, ensuring that the global minimum is achieved. Third, while the standard implementation uses a 2D DP table, we can optimize space further. Since the cost of painting a house only depends on the costs of painting the previous house, we only need to store the results for the current and previous houses. This allows us to reduce the space complexity significantly by replacing the full DP table with just two 1D arrays or even a single array that gets updated iteratively. To implement the optimized approach, we start by initializing a 1D array called previous to store the costs of painting the first house in each color. Then, for each subsequent house, we calculate the costs for each color using a temporary array cur. For example, the cost of painting the current house red is calculated as the cost of painting it red plus the minimum of the costs of painting the previous house blue or green. Similarly, we calculate the costs for blue and green. After processing the current house, we update previous to hold the values of cur, effectively shifting our focus to the next house. Once all houses are processed, the result is the minimum value in the previous array, which now holds the costs of painting the last house in each color. This approach ensures that we calculate the result in linear time and constant space, making it highly efficient. Before wrapping up, let's consider a few edge cases. If there is only one house, the solution is simply the minimum cost of painting that house in any color, as there are no adjacent houses to worry about. If all painting costs are equal, the algorithm still works correctly and will return the expected minimum cost. For large inputs, where the number of houses is very high, the optimized algorithm handles the problem efficiently due to its O(n) time complexity and O(1) space complexity. These considerations ensure that the solution is robust and performs well across a variety of scenarios. This solution efficiently calculates the minimum cost to paint a row of houses under the given constraints. The function minCost takes an input costs, which is a list of lists where costs, I, represents the cost of painting the ith house in red, blue, or green. The algorithm follows a dynamic programming approach using a rolling array technique to keep space usage minimal. 1. Base case handling. If the input list costs is empty, the function immediately returns 0 since no houses need painting. 2. Initialization. The variables prev_red, prev_blue, and prev_green are initialized to the costs of painting the first house in red, blue, and green, respectively. These represent the cumulative costs of painting up to the first house. 3. Iterative calculation. The algorithm iterates through each house from the second one, index 1, to the last. For each house, it calculates the cost of painting it in each color. To satisfy the constraint that no two adjacent houses have the same color, the cost of painting the current house in a specific color is the sum of the cost of painting it in that color and the minimum cost of painting the previous house in one of the other two colors. Cur_red. Painting the current house in red is the cost of red for the current house plus the minimum cost of painting the previous house in blue or green. Cur_blue. Similarly, the cost of blue involves the minimum of red or green for the previous house. Cur_green. The cost of green uses the minimum of red or blue for the previous house. For rolling update, after calculating the costs for the current house, the prev_red, prev_blue, and prev_green values are updated to the current costs. This ensures that only the most recent costs are stored, keeping the space complexity O(1). 5. Result. After processing all houses, the minimum of prev_red, prev_blue, and prev_green gives the minimum total cost to paint all houses while adhering to the constraints. This approach is highly efficient with a time complexity of O(n), where n is the number of houses, and a space complexity of O(1) due to the rolling array optimization. Here, we begin by defining the minCost method, which takes a 2D array costs as input. Each row in this array represents a house, and each column represents the cost of painting that house in red, blue, or green. The first thing we do is check if the input is null or empty. If so, we return 0 since there are no houses to paint. Next, we determine the number of houses, n, using the length of the costs array. We then initialize three variables, prevRed, prevBlue, and prevGreen, to the costs of painting the first house red, blue, and green, respectively. These variables keep track of the minimum cost of painting up to the previous house for each color. After this, we enter a loop that starts from the second house and iterates through all the remaining houses. Inside the loop, for each house, we calculate the cost of painting it red, blue, and green. For instance, the cost of painting the current house red is the cost of painting it red plus the minimum cost of painting the previous house either blue or green. This ensures no two adjacent houses have the same color. Similar calculations are done for blue and green, and these values are stored in cur_red, cur_blue, and cur_green. Once the current costs for each color are calculated, we update the prevRed, prevBlue, and prevGreen variables to the current costs. This prepares them to be used for the next house in the iteration. After processing all the houses, the loop ends, and the final step is to return the minimum of the three values, prevRed, prevBlue, and prevGreen. These represent the minimum costs of painting all the houses, ending with the last house painted in red, blue, or green, respectively. By taking their minimum, we ensure we get the optimal solution. This completes the implementation of the algorithm, which uses dynamic programming to solve the problem efficiently with a constant space complexity. To begin solving this problem, we start with the first house. The costs for painting it red, blue, and green are provided as 17, 2, and 17, respectively. We initialize three variables to represent the previous costs. Prev_red is set to 17, Prev_blue to 2, and Prev_green to 17. Now, moving on to the second house, which has costs of 16, 16, and 5 for red, blue, and green, respectively. To determine the minimum cost for painting this house red, we add 16 to the smaller of the previous blue and green costs, which gives us 16 plus 2, resulting in cur_red being 18. Similarly, for painting it blue, we take 16 and add the smaller of the previous red and green costs, both being 17, resulting in cur_blue of 33. Finally, for green, we add 5 to the smaller of the previous red and blue costs, yielding 5 plus 2, resulting in cur_green of 7. After calculating these, we update the previous costs to Prev_red equals 18, Prev_blue equals 33, and Prev_green equals 7 to prepare for the next house. Now, we move to the third house with costs of 14, 3, and 19 for red, blue, and green, respectively. For painting it red, we add 14 to the smaller of the previous blue and green costs, which are 33 and 7, resulting in cur_red being 21. For blue, we add 3 to the smaller of the previous red and green costs, which are 18 and 7, giving cur_blue as 10. Finally, for green, we add 19 to the smaller of the previous red and blue costs, which are 18 and 33, resulting in cur_green being 37. At this point, we update the previous costs to Prev_red equals 21, Prev_blue equals 10, and Prev_green equals 37. With all houses painted, the minimum cost is determined by taking the smallest value among Prev_red, Prev_blue, and Prev_green, which is the minimum of 21, 10, and 37. This gives us a total minimum cost of 10. In this next example, we consider a scenario with only one house. The given costs for painting it red, blue, and green are 7, 6, and 2, respectively. Since there's only one house, we simply initialize Prev_red, Prev_blue, and Prev_green to 7, 6, and 2, respectively. The minimum cost in this case is straightforward. We take the smallest value among these three, which is the minimum of 7, 6, and 2, resulting in a total cost of 2. Now, for the following example with three houses, the costs for the first house are 1, 50, and 50 for red, blue, and green. We initialize Prev_red, Prev_blue, and Prev_green to 1, 50, and 50, respectively, and proceed to calculate the costs for the subsequent houses. The second house has costs of 50, 1, and 50 for red, blue, and green, respectively. For painting it red, we add 50 to the smaller of the previous blue and green costs, both being 50, resulting in cur_red of 100. For blue, we add 1 to the smaller of the previous red and green costs, which are 1 and 50, giving cur_blue of 2. For green, we add 50 to the smaller of the previous red and blue costs, which are 1 and 50, resulting in cur_green of 51. We update the previous costs to Prev_red equals 100, Prev_blue equals 2, and Prev_green equals 51. Now, for the third house with costs of 50, 50, and 1, the cost for red is calculated by adding 50 to the smaller of the previous blue and green costs, which are 2 and 51, resulting in cur_red of 52. For blue, we add 50 to the smaller of the previous red and green costs, which are 151, giving cur_blue of 101. Finally, for green, we add 1 to the smaller of the previous red and blue costs, which are 102, resulting in cur_green of 3. We update the previous costs to Prev_red equals 52, Prev_blue equals 101, and Prev_green equals 3. The minimum overall cost is the smallest value among these, which is the minimum of 52, 101, and 3, resulting in a total cost of 3. To analyze the time complexity of our solution, we can break it into three main steps. First, during initialization, we assign the costs of painting the first house to three variables: Prev_red, Prev_blue, and Prev_green. Since this is a simple assignment operation, it takes constant time, or O1. Next, we iterate through the remaining N1 houses. For each house, we calculate the cost of painting it in each of the three colors, red, blue, and green. To do this, we take the minimum of the costs from the other two colors of the previous house, which involves 2 comparisons per color. Since there are 3 colors, this results in 6 comparisons per house. Along with updating the variables for the next iteration, the total time spent per house remains constant, or O(1). When we consider all N1 houses, this step contributes O(n) to the overall complexity. Finally, at the end, we return the minimum of the 3 computed costs, which again takes constant time, or O(1). When we combine these steps, the overall time complexity is determined by summing up the complexities of initialization, iteration, and the final computation. Initialization and the final computation each take O(1), while the iteration over all houses contributes O(n). Adding these together, the total time complexity becomes O(n). Now, for the space complexity, we only consider the additional memory used by the algorithm relative to the input size. Since the input costs array is provided, it doesn't count toward space complexity. The algorithm uses 3 variables to store the costs of the previous house and 3 more variables to compute the costs for the current house. This totals to a constant number of variables, independent of the number of houses. Thus, the space complexity is O(1). To better understand the efficiency of this solution, let's compare it to a brute force approach. In a naive solution, we could recursively explore all possible combinations of painting the houses, ensuring no 2 adjacent houses share the same color. For n houses, this would result in 3 choices for the first house and 2 valid choices for each subsequent house, leading to 3 times 2 raised to the power of n1 combinations. This approach would have a time complexity of O(2 to the power of n, which grows exponentially and becomes infeasible for larger inputs. In contrast, the dynamic programming approach we've implemented reduces this exponential complexity to O(n) by iteratively calculating the minimum cost for each house and only storing the results of the previous house. This optimization is possible because the problem has overlapping subproblems and an optimal substructure, key characteristics that make it ideal for dynamic programming. Additionally, the space complexity is reduced to O(1), since we don't need to maintain additional arrays or recursion stacks. This makes the current solution both time and space efficient. To formally verify the time complexity is O(n), consider that the number of iterations is directly proportional to n, the number of houses. During each iteration, we perform a fixed amount of work, calculating costs for 3 colors, making comparisons, and updating variables. Since this work is constant and independent of n, the total time complexity scales linearly with the input size, resulting in O(n). Similarly, the space complexity is confirmed as O(1), because the algorithm only uses a fixed number of variables regardless of the input size. These factors demonstrate that the solution is optimal in both time and space complexity for the given constraints, making it highly efficient for solving the problem of minimizing the cost of painting houses. One of the most common mistakes in solving the paint house problem is not accounting for edge cases. For example, if there are no houses to paint, or if there's only one house, the logic can fail if these scenarios are not explicitly handled. Always validate your input constraints to ensure these edge cases are covered. Another frequent issue is confusing the state variables in your dynamic programming solution. It's crucial to distinguish between the cost of painting just the current house and the cumulative cost up to that house. Mixing these up can lead to incorrect state transitions. Additionally, forgetting to memorize results or recomputing the same subproblems can significantly increase the time complexity. Properly utilizing your DP table or cache is essential to avoid unnecessary calculations. When using recursion, defining accurate base cases is critical. For instance, when no houses are left to paint, the recursive function should return 0. Failing to handle this can lead to infinite recursion or incorrect results. Finally, overcomplicating the problem by using brute force or convoluted logic to handle constraints, such as ensuring no 2 adjacent houses have the same color, can make the solution inefficient. Instead, focus on simplifying the problem through clear and logical state transitions. In an interview setting, it's often beneficial to start with a brute force approach to show your understanding of the problem. From there, you can gradually optimize your solution by introducing dynamic programming or other techniques. A key part of this process is clearly explaining your state transitions. For example, you might define DP, I, J, as the minimum cost to paint up to house I with color J. Clearly articulating what your state variables represent and how they transition is crucial. It's also important to focus on the constraints of the problem, such as ensuring no two adjacent houses have the same color, and to demonstrate how your approach respects these rules. Space optimization is another valuable skill to highlight. For instance, if your DP solution can be reduced from O(n*k) to O(k) space by storing only the results for the last house, mentioning this shows that you're mindful of efficiency. Finally, be prepared to adapt your solution for common variations, such as additional constraints or dynamically updated costs, as this demonstrates versatility and a deep understanding of the problem. There are several related problems that you might encounter, which share similarities with the painthouse problem. For example, LeetCode 256 is a simpler version of the problem where there are only 3 colors to choose from. LeetCode 265, on the other hand, is a more complex variant where the number of colors is not fixed, making the problem more challenging. Another related problem is LeetCode 198, the house robber problem, which also uses dynamic programming but focuses on maximizing profit with non-adjacent constraints. Finally, LeetCode 931, the minimum falling path sum, deals with minimizing path costs across rows, and while the context is different, the DP concepts are similar. When it comes to alternative approaches, brute force is one option, where you enumerate all possible configurations to find the minimum cost. However, with a time complexity of O(k) to the power of n, this quickly becomes infeasible for larger inputs. It's useful as a demonstration of the problem but not for practical solutions. A better approach is top-down DP with memoization, where you use recursion and cache results to eliminate redundant computations. While easier to implement, this method can have higher space usage due to the recursion stack. Another efficient approach is bottom-up DP, where you iteratively fill a DP table to compute the minimum cost. This has a time complexity of O(n*k) and avoids the overhead of recursion. For even greater efficiency, you can optimize the space usage in your dynamic programming solution by reducing it to O(k). This is achieved by maintaining only the last row of the DP table instead of the entire table. By doing so, you significantly reduce memory requirements without compromising the correctness or efficiency of the solution. This space-optimized approach is especially beneficial for scenarios involving very large inputs, where conserving memory is critical. It's a great way to demonstrate your understanding of advanced optimization techniques and your ability to adapt solutions for practical constraints. Great job on completing this problem. To summarize, we explored the painthouse problem and discussed how dynamic programming can optimize the solution. Remember, mastering DP takes practice, so keep challenging yourself with similar problems. Thanks for watching. Don't forget to like, subscribe, and share to support the channel. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!